The next speaker is Shankar Ghosh, Desorption to delamination, dynamics of detachment in a thin film.
Thank you. This talk is going to be one more talk on failure. I don't know the connection, whether it has anything with nucleation or not, but it's going to be a talk with failure, and that's connected to the previous talk. So desorption to delamination. Initially what I'll go and do is I'll define processes which is like desorption. I can't give you a proper definition of what desorption is. I'll explain processes which is like delamination. And these are ubiquitous things in nature. You can just go up and see anywhere, here or not. But usually it's on the walls paints which peel off. And dynamics of detachment is something like if I, for example, take a peel of tape and put a load onto it, and after some time it peels off. So there's creep, there's time involved in it. In my experiments, we have actually dealt with detachment, but just for the completeness sake, I will talk about adhesion, dynamics of adhesion in a thin film, and in some convoluted way, I'll say that if I know about adhesion, I can say something about detachment. And let me just first thank my collaborators, Atul, who is here, who has mainly done this work on desorption to delamination, Prerna, who has worked on, these are two graduate students who has worked on adhesion problem, and Shobha, who has been with the group from its very first stage of the problem. So what's desorption? Desorption is I have a surface, for example, say this one, which is spheres on a plate. I apply a stress on it, and the system reaches a critical stress, and things come out. If they come out one at a time, it's like a popcorn coming out from a hot plate, or a gas desorption, a hydrogen desorption from palladium. I say this is desorption because the events are single particle events. There is no large scale correlation, structural correlation in the parts that have come out. Okay. What is delamination? Delamination is something like, for example, if I had this thing stuck to a plate and I pulled it, or I had applied stress to it, the system failed, like paints come out. That's delamination, and the difference between delamination and desorption is mainly at the length scales of it. Well, there is a stress level also. Usually desorption happens at stress levels which is much lower than that at which delamination happens. But in delamination, you have a length scale where the system size spans many particles. Desorption, the system is the failed structure is typically 1 to 2 particles. Okay. It's a very complex problem. Look at, if you deal with this problem, look at this structure. Now, this is just to do a few, and biologists will tell you, I have cell delamination in cell and whatnot. How do I deal with this problem? It's a no-starter even to think about. This is a concrete block which is split off. This is a PCB board which anybody who has worked and experimentally knows that if I put the soldering iron for a long time, these strips actually come out. This is wood. Okay. So these are the questions. Can I? I'm an experiment, so I'll say that, can I go up and find out a simple model system? Maybe a hydrogen atom of the whole problem. Something which I can say some statements definitively about. Okay. And something which will show me the most of the, a richness about what you see in the nature. Not necessarily that it makes one-to-one correspondence. Okay. Can I describe this whole parameter, the whole phenomena, this kind of phenomena in an experiment with few parameters? Let's not come up with, hundreds of parameters and describe every system, but a simple system which I can tune the system from going from desorption to delamination and describe the system in terms of few parameters. Few parameters, one which is observable, the others which is measurable. And observable parameters comes out straight away. In desorption, there is one nice thing about desorption and delamination. The observable parameter is the length scale. And that we know. We can just see something, and that's the length scale at which the system has fails. Can I draw up analogies? The purpose of drawing up analogies is, it's a difficult problem. If I can draw up analogies, maybe I'll be able to learn from some another field what they have already made stories about in that particular, an understanding about the phenomena in some other field. So the kind of fields that I would like to make connections to is disordered elastic medium, plasticity, wrinkling, pinning, cracking, and maybe to the whole problem of jamming. Okay. Okay, what is the observable parameter? Observable parameter is length scale. Now let me try and come out that this is actually a very nice thing, because for example, let me take a film, which is put onto this surface, and I have glued it out, and say this film was actually very, very soft. I apply a stress on it. What will happen? The things will fail, and they will fail at a length scale which is actually individual length scale, because the structure is so soft that it will not be able to support it. Okay. Now if I had this film which is infinitely rigid, so say I had a metal film which I put onto this plate with a soft glue, and I tried to pull it out, the whole thing will come off together. It will not break into pieces. So length scale is something which comes out as a competition between your thin film, which is up there. So this tells you thin film, which is characterized by some Young's modulus, bulk modulus, whatever, elasticity modulus, which kind of energy per unit volume. I have an adhesion strength in the whole system, which is somewhere here, which is in the interface, and that is something like energy per unit area. And I have again the substrate, I can pull it off, and the substrate might itself also crack, but for now I'll assume that the substrate is so rigid that nothing happens to the substrate. So for some critical values of stress, I get a length scale over which the system fails, and I say, well, maybe it depends upon this G, which is the elastic properties of the thin film, and the adhesion potential. This is just put in just by hand. I'm not going to, at the end of this story, maybe I'll tell you definite statements about it, but let's just put it by hand. Let's say, well, it depends upon G and FP, and if my FP is very small, I can argue, well, if my pinning potential is very small, which is just to tell that I'm very weakly pinned a surface onto a plate, I stress it, the whole thing comes together. So xi is very large. If FP is very large on the other sense, that if I have pinned it very hard, I try to pull it off, it will break into small patches, and that means that xi is small, the length scale is small. If the material is very rigid on the top and it fails to fail, well, it's very rigid, it just keeps its registry, I'll pull the whole thing together. So essentially, if G is very large, xi is very large, and it will span the whole system. Okay. So what are the, so if I want to do an experiment, what are the control parameters that I want to have? I want to apply stress in a controlled fashion way. I want to alter the rigidity in the system, the adhesion of the system. Now the problem is I also want to know what is the nature of G, because in nature not everything is elastic, it's viscoelastic. For example, if you have a cell which is adhered to the substrate, the coupling is not elastic, it's viscoelastic. I want to observe events which spans from single particle length scales to large particle length scales. I should be able to do it under a microscope and simultaneously observe such large scale of events. And I want to figure out a model system. So this is the plan of the talk. So I will first describe single particle events, failure of single particles events, which is adsorption of, and this I will talk in a little bit convoluted way. I will talk about adsorption and desorption of single particles to glass plates, which is colloidal particles. I will take colloidal particles, put it onto glass plates, apply stresses on them in a controlled fashion way, and see at what length scale the system fails. Okay. Just a brief liner, because I will use some terminologies here and it's nice to put them on. If I had a spring and if I stressed it, so I put a stress, I know the stress is proportional to strain, and the proportionality constant comes out with something which is called as a G prime of the system. If I have a system which is liquid-like, and then I have something where the stress is related to strain, actually it's related to the strain rate, its strain rate and the proportionality constant is G double prime. So G double prime is like a rigidity, imaginary part of the rigidity modulus, which gives you the measure of viscosity of the material. Whenever I talk about G prime, I am talking about the elasticity of the material. So typically for an ideal solid, you have a G prime which is frequency dependent. So G prime is 0, and G double prime is something which is like the viscosity of the liquid. Okay. So this is the experiment. So what I do is I put in, let's see up here, I put in colloidal particles onto an ITO. So this is an indium tin oxide glass plate, coated glass plate. It's conducting. I put some colloidal particles on the top of it. I allow them to dry, and after they have dried, I put some oil between the spacer. There's some 100 micron spacers up there. I put an indium tin oxide plate again on the top of it, so it's a parallel plate capacitor. I place and apply an electric field to it. And these are polystyrene particles. I'll show you what it is. So as I apply the electric field, and these are terms in terms of voltages per 100 microns, I start seeing individual events. So you'll just see that there will be particles which will start popping out of the plate. So you start seeing the particles which just pop out of the plate. So this particle this is just, the other particles have gone out of focus. I'm just imaging just one plane, the particles have gone out of focus. So this is an event where I see desorption, and the length scale is one single particle event. Now, I'm going to look at the opposite part of it. So I'm going to first explain a system in which I take a colloidal particle and try to stick it to the plate, because see this, suppose I had applied, now what I did was I swept the stress. I took the particles up here, applied an electric field. These are dipolar particles. The moment I apply an electric field, there's an induced dipole moment upon it, and so they apply a stress on them, and they want to align up in this direction. That's the reason why the particles leave this plate. Suppose I had left the particle on with a particular field, so I have not swept the field, I went to a critical field and just waited there. Then I would have seen creep events in my event. So the particle would still have gone about without my increasing the field. So to look for that, I'm going to look at a problem which is the adsorption of the colloidal particle to a glass plate. I'm going to take a single colloidal particle and try to stick it to the glass plate and see what is its physics about. So this is the reverse of the problem of what is the time involved for the particle to come out of the plate. So if you look at a particle which is in a liquid, for example, now I'm going to, if I could run this movie backwards. For example, now this particle is in the liquid, I would run the movie backward, I would find the particle going back to the substrate. Now, when a particle is in a liquid form, this particle is coupled to its environment by viscosity. So this particle gets kicked from the environment by viscosity. So if I measure the G prime of the system, the system is somewhere up here. It's a red spot up here, which is the G double prime is finite. There is no elasticity in the system, and the particle is somewhere here. If I measure this system when the particle has got actually stuck to the plate, then the coupling of the particle with its environment is elastic in nature. So essentially the particle is up here. If I move the plate, the particle will move with the plate. So the system transits from somewhere here to somewhere a spot up there, which tells that G prime is finite. The system has finite elasticity, no viscosity in my system. You can ask these questions like, what does it mean to get a particle stuck? Well, how do I define the particle has got stuck? How do you study the dynamics of sticking? And differences between sticking of rigid and soft particles. So what does it mean that if I have a rigid particle, if I had, for example, metal on a metal coupled by some glue, which is also, which is a crystalline surface, which is like epitaxy growth of one metal on the other metal. How does it, so various parameters. I'll take that's what's done. So if you take a particle up there in a liquid, in the bulk, the particle is making some Brownian diffusion, and this is some finite diffusivity. If I bring the particle close to a glass plate, then essentially what happens is the diffusivity falls. This is just hydrodynamics correction, and it goes to 1/3 of its value. But if the particle gets stuck to the plate, then the diffusion coefficient goes to 0. So the particle is absolutely not diffusing. So diffusivity is a good measure. And how do you do that? Well, what you do is you trap the particle in an optical tweezer. So you apply a small spring to the particle. You oscillate the whole thing. So this is a particle which is trapped in the liquid. The whole thing is in a container, and I oscillate it. Now, if a particle is up there in the liquid and I oscillate the whole system up, the motion of the particle is with a phase difference with respect to the liquid's motion. So because the stresses are transmitted to the particle through viscosity of the liquid, and viscosity has an omega times xp dot, which is basically the plate's motion. That's the velocity. So there is a phase difference between it. Once the particle has got stuck to the plate, then the particle is moving in phase with the system. So essentially phase is a very nice measure of whether the particle is stuck to the plate or not. A non-stuck particle has a finite phase difference, a stuck particle has 0 phase difference. Okay. So what you do is you basically take a particle in the system, oscillate the whole thing, measure the phase difference. A stuck particle moves in phase, so there is no phase difference between the particle and the container that you have, a closed container. And you can and then you can model this whole thing in terms of a G prime and a G double prime, and you can measure G prime and G double prime from your experiments. No, I just no the kbt over no. Sorry, that's friction coefficient. That's friction coefficient. This xi is not length. Sorry, this is because it's taken from another slide. So that's the friction, which is 6 pi eta a for your steel. That's not length. Sorry. Okay. So this is your system. So I have a system in which I have a particle up here. I'm driving the particle. This is an experimental setup. Because of shaking of the whole system up here, I have a drag on the particle. There is a trap. So basically there is a k optical thing which is holding the particle back to its position, and there is a friction with the environment. That's all the system is about. And I will split this friction with the whole environment in two terms. One is the elasticity, and one is the viscoelasticity. So essentially when the particle is on the plate, then the coupling is elastic. So K friction has mainly terms from the elastic coupling with the plate. And when it's in the liquid, it's mainly viscosity, and so the coupling is mainly viscous in nature. Okay. So this is your data. So once the particle is in the system, so you can see this is a hard particle, which is a silica particle, and this is a soft particle, which is a polystyrene particle. And this is a little odd way of plotting. What I have plotted up here is height of the particle from the plate. So I take a particle, bring it to the plate, and then just leave it. At this point, I don't move the plate or the particle anymore with relative to each other. This is only time. This is the time dependence. So once I have a hard particle, the particle is up here. The tan phi is a measure of how good the particle has got stuck. If I take a silica particle, the moment it comes to the plate, boom, the phi goes down. And basically it says that the particle has got stuck immediately almost. If I take a polystyrene particle which has hairs on the top of it, then there is a lot of time involved in the whole thing. So you can see this is macroscopic time. It's 20 minutes, 30 minutes. It sometimes can go really long. And the tan phi slowly dribbles down. And if you look carefully into this, and you'd see that this phase the thing doesn't go down in an exponential manner. It will hover about in a particular space, and then suddenly make a transition to another value, again hover about at a tan phi for a different phase. So it means that the G double prime or the G prime are making constant changes from one particular parameter space to another parameter space. So you can see this glitches up here. Okay. So this is another way of plotting G prime and G double prime. This tells you that if I take a polystyrene particle with time, now, the G double prime becomes finite, the G double prime becomes 0, and the G prime becomes finite, which tells you that the coupling has gone from an elastic to from a viscous to an elastic regime. So this was viscous mainly, the elastic part being 0, here the elastic part being finite, and this is the viscous part being finite up here, and the viscous part being 0 at the end of the day. So how do you control all of that? Now, like desorption and delamination, in addition, can I control all of that? Can I make things behave different? Can I make polystyrene behave differently? Can I make polystyrene behave like a silica? Yes, you can do that because you can play around with the salt concentration, you can play around the frequency of the drive, and you can play around with the optical trap stiffness. Now, salt concentration, what it does is, these are silica particles or these are polystyrene particles. Most of them have some surface charges on them. And this is glass to start up with. This was not an ITO. So when you have a glass up here, you have a surface charge on the glass because it's an aqueous medium. So you have screening, you can screen the charges by putting salts, and you can do that. The frequency is not an obvious thing what it does. It's an experimentally found out frequency, does something to the whole thing. Optical trap stiffness is not, it's very easy. It's just because I hold the particle very hard, I will always make the particle slip. The particle can never stick. So it's like a loading force. It's like a static friction, how hard I push the particle. If I push the particle with infinite force, nothing can ever get stuck. So basically that's all that it says. And you can come up with a phase diagram. So you can make particles depending upon, this is again a simple polystyrene particle which behaves almost like a silica particle. So you can see that here the particle was up here, G prime. It made a sudden transition to G double prime. G double prime finite to a system in which G double prime is 0 and G prime is finite. This is again for each. You can make this whole system in which you can make a polystyrene particle behave in a very complicated fashion. So you can make a polystyrene particle behave like a silica particle somewhere up here, which depends upon the salt concentration. If I have high salt concentration, low frequency, low trap strength, then I can make a particle behave exactly like a silica particle. If I take an intermediate conditions, then I can make the polystyrene particle age. And if I take still more drastic, I would say, condition in which I have a large drive on the system, very low salt concentration in the system, and a large frequency in the system, then the polystyrene particle will never get to the plate, stuck to the plate. So what I mean by never stuck to a plate is something which you see when you do experiments, you take a polystyrene particle, the particle comes to the plate, and it actually never leaves the plate, it's tethered to the plate. It just keeps on hovering about at that particular point. So if I calculate the G effective, the G double prime is mainly coupled through the viscosity. The tethered elasticity doesn't come out, except that it gives you a saturation in your mean square displacement versus time. Okay. So now let me go to the, so this is the single particle events, and that's to do the time scale of the single particle event. Let me go to the many particle events. Can I look at the many particle events? Okay, this is the same experimental setup. I'm not going to deal with polystyrene particles right now. I've learned that polystyrene particles are soft particles. If I calculate the G prime from there, the G prime comes to a value of 2 to 5 pascals. It's a very soft interaction with each other and with the plate. So I'm going to deal with silica particles. And silica particles, because a priori I know in aqueous system, silica particles form SiO bonds with each other, and that's a covalent bond, which is strong bond. So what happens if I had actually made these thin films, which I showed initially, the popping up of the polystyrene particles, not with polystyrene particles, but with silica particles? And that way I would have altered my rigidity of my system. Okay. So I make this nice network of silica particles and not by polystyrene particles. This was measured to be 1 Pascal, and this we know from literature is of the order of 100 Pascals. This is not measurable by optical tweezer techniques. Okay. So this is what happens. So what you saw previously was single particles popping out, and now what you see is basically chunks which are coming out. That is field, what you see on the top up here, and now you see this whole thing coming off as they're breaking off into length scales, and they're just leaving the substrate. This is just because the flakes go out. It's a finite size system. They want to actually, to minimize its torque, they want to flip in this direction. But they also overlap between two flakes. And so you see dark regions. And this is the region through which light is coming out, the white region through which light. The two things that we found out of these cracks is usually you have Y-shaped cracks. And that's always true. You always tend to have Y-shaped cracks. These are disordered material. I mean, if I went up and plotted for you a G of R, it looks almost like a disordered material. So there is no order in the structure. And you can look at it, these are 4 micron polystyrene silica particles. They sediment very fast. So the Peclet number is such that you don't get any kind of an ordering of the system. This is very disordered structure. This is amorphous structure to start with. But you still get, because of local symmetries, probably you still get a Y-shaped thing. If you are interested in, you can go up and do a crack analysis of it, and you can find out what is its fluctuations of Z max from its mean value with respect to the length, the window size, and it gives you a critical exponent of 0.8. And this is to show that every time you have a crack, so this is like zero field, and then you initiate the field, you have a Y-shaped crack here, then you have again a Y-shaped crack here. You can see that the crack is initiating somewhere here, which actually grows at a larger field to this. So it's essentially you have Y-shaped cracks, the cracks open, then you have an electric field which wants to, so if I have a flake like this is unstable equilibrium. This is the stable equilibrium because it's an anisotropic object, and the polarization will be such that the torque will be minimized if I just go up in this direction, and that's why the whole thing flips. So otherwise you'd see that once it has cracked, there is no reason for it to flip.
There is no uniform length scale, right? Because all the pieces that have come is different.
Absolutely. So I have not shown you the plots of the length scale. But this thing, now, just because you know the scale bars also, tells you it's very different from a single particle event. You know it's a many particle event. True, you don't know what exact length scale you have. The length scale also has a spread on it. Perfect. True, the length scale has a spread on it. And I'll show you that the spread is far less than for various other systems. Yeah. And there's also another problem, it's an experimental problem. So the problem is, if you have a large length scale thing which wants to flip like this, then just because you have a boundary on the top, which is 100 micron, it cracks. So sometimes these cracks are secondary events. It has, after it has flipped, the things have actually cracked. Okay. So now what I do is, since I did polystyrene and since I did silica, I go up and do a mixture of it. So if I have 100% polystyrene case, I know what I will have. So this is the main emphasis here is to try to look into the viscoelastic regime. So But if I have a finite volume fraction of silica in the system, then the silica will hope that it makes percolating clusters and they kind of hold them together. But they are not rigid clusters, so probably they will actually deform, and you can see some I would say closeness to what you would see of paints coming off from film. So these are like viscoelastic objects. These are soft objects which will not feel like cracks, straight cracks, linear cracks, but which will slightly deform. And you will say that, I have a form, it deforms, it still deforms more, still till the point that it hits a plasticity and the system flows. Okay. So this happens. Suppose I take a 0.5 volume fraction of silica and polystyrene mixture. Then the failure event is very different. Then you start having blisters in the system. These are the blisters which you actually see. If you go outside, you will see blisters on the wall because they are polymer paints with colloidal particles loaded in. And when they fail, that's because moisture has gone in, and with time they have placed stress in it. Time is not explicitly said in my system. I've just showed you that time plays an important part. It's difficult to quantify time in this particular experiment. So no creep experiments have not been talked about here. You've done it, but we'll not talk about it. So I have a film like this. I apply stress. It forms nice blister-like. The blisters actually flow with time. And then after a point, the blisters give away and they just tear apart into small pieces. So that's the way the system fails. Okay. So what we did is we took two single particle events and we showed that if I have a very small volume fraction, I've not given you the data, I'll show you now the data. So if I have a volume fraction of silica which is less than 0.3, I tend to have single particle events. This is mainly like things popping out of a plate. If I have a mixed regime, I put volume fraction of silica which is larger than 0.3. And till about the point it's like 0.8. I don't know what's the significance of this 0.8. Then I tend to have blisters in my system, which is something like this. So you can have small blisters. This is not the image. This is just to say what nature would look like. And if I have large volume fractions of silica, which is greater than 0.8, you essentially have linear cracks and the system fails as like really rigid objects. So you can do something better. Now you can plot the area that has been delaminated. So this is a well quantified number. I know how much of the area has delaminated out. This is not the length scale. This is just the area which has come out of the plate as a function of my stress. So I'm plotting E, but E square is my stress. Half epsilon E square is my stress. So if I plot the electric field on one axis, the other axis is just my area delaminated. For example, if a flake comes out, that white part is the whole thing which has got delaminated, so I can normalize it with my rest of the image. So that's what. So if you have single particle events, then it's mainly like this. It's a runaway event. So one particle comes up one at a time. And there is no markers of any sharp features on it. If I have silica particles, for example, up here, 100% silica, thing goes up. I have a flake which comes out, and nothing happens for some time. I increase my field to another field. It crosses the critical field, another big flake comes out. So this is basically gives you very sharp transitions in my. So if I plotted the derivative of it, this would be like a continuous thing, and this would be very sharp features. And anything of like this would give you a hallmark of collective process. Collective process is things where many things happen at a time. So your effective area or the area of delamination changes suddenly by a factor. So you can see that even when I have somewhere at 0.5, I still have signatures of collective events up here. So both collective and individual events happen here. This is the scale that you are talking. This is the error bar. So you can do this analysis and you can put error bars on your length scale is not of one defined quantity. If you are at a low volume fraction, then your error bar is very small. It's single particle events. This is mainly single particle events. If you're up here, your error bar is a log scale, so that error bar is not that small. You have an error bar, but it's also not very large. So essentially, if I change my volume fraction, I can go from single particle events, which is like 1. A naught is my radius of the particles. So this is the diameter of the particle actually. Xi naught by A naught is 1. If I do 0.2, it's also 1. I sometimes have two events, two particles coming out simultaneously. If I up here, then I have hundreds of particles which come off simultaneously. Somewhere down here is actually an interesting area where you have blisters. And here you have blisters of various sizes happening. Some blisters are large, some blisters are small. This is an area where we believe that you have competition between both collective events, small events. Percolating size clusters are of different sizes, and that's the reason why you have this. We have not looked very carefully. So this is just log scale, and that's why you're seeing it. The error bar is looking at a not symmetric. So, on a log scale,
Some of them have asymmetric the other way.
which way? This one? I believe if it is just the plotting, otherwise it's asymmetric. If I plot it on a log scale, it should be symmetric. Yeah, in a linear scale, it should be symmetric. So it's just plus minus error bar. Okay. You can go up, and if you're bold enough, you can just plot the EC square, that's the stress versus my xi naught, which is the length scale at which the system fails. Well, if my length scale increases, or if my critical failure increases, xi naught increases, nothing more than that. I don't know whether it's linear or not, but it increases generally. Okay. Now you can ask this question. You see, suppose I had a paint which is put on, and the paint is not of a good quality. I put it onto a wall, and the paint starts peeling off the next day. This is another good quality paint that I put on a different wall, and that paint starts peeling after 10 days. Okay. I come after 200 days, and I ask this question, how much of the paint which has been peeling off from the weakly coated wall, and how much of it has been a well-coated wall? And this is the question that I'm going to ask here. My answer is, if you have a poor quality paint painted on one wall, yes, initially it starts failing, but then it will hold on to some small patches, and the fraction of the area that will hold on to it under large time limits will be the same after the other film has also peeled off. So I'm going to plot something which is like this. I'm going to call out an expectation value of my electric field, which is something. I'm going to say area. Let me ask, what is the average field at which 0.1 fraction of my film has got delaminated, at which 0.3 fraction of my film has got delaminated. So this is saying that, I have a 0.1 fraction of the film has delaminated. So initially at very low fields, things start getting delaminated, popping up. This happens at a much larger field, but everything almost happens very close by to each other in a correlated structure. So this is what you get. If I took my threshold area to be very small, if I said only I'm bothered about only where the first failure events happen, then this thing increases, EC square, which is the stress, increases, critical stress, increases dramatically with my volume fraction. So it's a very sharp increase. This is another measure of actually the error bar in some way. You can see this again. So it goes up very dramatically. But suppose I ask the other question. I chose not the 0.1 as just the initiation, but I said, okay, how much when 30% of my film has got delaminated, what happens then? But I've asked this question. It so happens that that's not so dramatic. Yes, it increases, but it doesn't increase that dramatically. And what it tells you is, these two are measuring two different parameters of my experiment. What this measures is my elasticity of my thin film. It tells you that, the first crack is where the elasticity of this thing has failed. Plasticity has come in. This tells me where actually the things have overcome the maximum pinning of the potential. So I can have a small failure. The system, there's a small crack up here, and I get the light coming in, so I measure this thing. But if I want to flip this out, a large thing totally up, then I have to overcome the deepest potential minima that this flake is in. And since both of these films are on ITO, I don't expect the adhesion potentials to be dramatically different. The adhesion potential is similar. So this parameter, the red line, red spots, are a measure of what I would say is my adhesion potential. These blue spots are a measure of what I would say is my elasticity. So let's say this, well, the system fails. But if I think what are the last flakes which are actually sticking onto this plate, that is what will give me this part. Those things to overcome, because it has already failed, the system has already given away, will only come out when it has overcome its deepest potential minima. And hence, both of them are actually similar. And this is some average value that you have. You can say, well, I'll not do all of this with polystyrene, but if I can do only with silica. So you can go and choose the system and do it, prepare it at various pHs. And chemists know that if I develop systems at low pH, then bond dissociation at SiOH is lesser. So I basically have lesser amount of covalent bonds. So I will have a weaker structure. So you can do all of that, and then it says that a system which is at a low pH is of low rigidity. So essentially you have a smaller xi naught by A naught. If I develop a system at a high pH, it's of a higher rigidity, and have a system which is xi naught by A naught, which is large. So essentially, even if you did just with silica particles and not mixed it with polystyrene particles, you still hold the behavior to be same. What about creep? All of these are known to have creep events. So say I went and sat very close to my critical field, I just waited there, things would fail. I will not talk about creep events here, just I had motivated you to say that even adhesion has a lot of time independence in it. Just because it's very difficult to define what a critical field is. How close to a critical field do I sit? This is an experimental problem. Where do I choose? For example, here, experiment to experiment, my critical field also has an error bar. So it's difficult to a priori know when I have made a film where this film is exactly going to fail. Film to film it will change, even if it's by few percent. But that few percent reflects very strongly when I look at the creep behavior. So if I am within 1% within my electric field, then I get a different kind of a creep behavior. When it's slightly less than that, I get a different kind of creep behavior. But we know that creep is a very important problem in all of this. So what sets up this length scale? So what sets up this length scale is this. For example, if I had a thin film which is being deposited, just the act of deposition causes crumpling of the thin film. And if I apply stress onto this, now I have not applied, so what is this crumpling has happened when I was actually depositing this thin film onto the substrate. And I've already pre-stressed this thin film. So apply stress, and this is going to fail at wherever I have ridges. So wherever I have this up here, if I apply stress, it is going to tear from one of those things. Now, and what sets up this length scale? Between the folds of this crumpled paper is a competition between the adhesion potential and G. And this is well known in the context of vortex physics. So what you do is you just take a lattice without a substrate. It could be any reference lattice. Put it onto a substrate. The lattice is going to strain itself to accommodate the substrate on which it's falling. And so this lattice will get strained out. So you imagine that this is a lattice, a perfect lattice. I put it onto a substrate, which is like a pinning potential. And this object now has to satisfy not only its nearest neighbor, but also the substrate at the bottom. So it's going to strain. So this doesn't have to be a perfect lattice. This can be any reference lattice. You take a reference lattice, put it onto any substrate, the reference lattice is going to get strained up. And once it gets strained up, you create this creases onto the system. And so a competition between your G and your FP, I mean, this is just to say that, is some that I have taken over by taking random additions of terms from various potentials, which is actually two-dimensional in nature. Sets up a length scale in your system. And this length scale comes just by minimizing your DF with some length scale in your system. And you get a length scale which is proportional to G and a length scale which is inversely proportional to W. So it tells you that W is something like my adhesion potential. So correlation length xi naught increases with rigidity. And I say already that the xi naught is prefix in the system. It doesn't depend upon the stress. So I increase G, my xi naught increases. I increase my FP, and this decreases with my pinning potential. So if I have a large FP, then my xi naught decreases. So essentially it tells that if I pin them at very close points with large pinning strengths, this is going to the distance between two pinning spots is going to give me the length scale at which the system is going to fail. You can say that, well, I can take a system in which I drive the system now. I stress is proportional to strain to the point that the system fails, and I'll put a critical value of stress and strain, and I substitute back the whole thing. And what you get is you can explain so G is proportional to this, and stress, which is like the critical stress now at which the system fails, is also proportional to this particular quantity. And these are the few parameters that you require to explain the whole thing. You require a adhesion potential, which you could have guessed earlier. You require a G, which is the elasticity modulus of the system, and the length scale, which is an easily observable parameter, and that will set up the whole game for you. So in the conclusion, what you say is, colloidal thin films are a good model system to look at this kind of failure events. In some cases, it's easy to see, for example, large delaminations, chunks delaminated to single particle events. Viscoelasticity, which you get by mixing the two systems, is a complicated event. You might be able to make some sense of it or not. This gives you only a few parameters in the whole game. So it gives you parameters like W, it gives you parameters like G, and it's an observable parameter, which is the correlation length in the system, of which the system fails, and it's an easy system which you can either see and connect it with your experiments. And because of this formalism, and which actually explains the data well, we believe, and this is only a belief, that it makes connection to larger class of problems. Thank you.
Questions?
So you may have said this during your talk and I may have missed it. When you mix your silicon and polystyrene particles, do they... Okay. When you mix silicon and polystyrene particles, do they arrange themselves in specific patterns, or are they uniform? Are they sort of...
Yes, they're all over the place. They don't phase separate. So if I take any small chunk, it's 50-50. Yeah, but there is no structure in it as such. This is an amorphous structure. It's truly amorphous.
Right. And in these different electric field regimes, when you make your mixtures, do you see a particular kind of particle popping out? Can you say that? So just you showed it for...
So particles which pop up, single particle events, are always polystyrene particles. Silica never pops out. Usually never. Silicas always come as small clusters. So they form small clusters between themselves and then they pop up from there. So you can have the length scale of silica which goes to small to large, but you will never see a silica doing the kind of things which you saw for polystyrene. Because if I had a film which is almost 100% 100% silica, they would come off as chunks. But however, in a mixture, whether a single particle silica even can happen or not, it's difficult. I can't say.
There's no parameter that you can tweak to get a rigid particle to do all of.
That's what we did, right?
Do all of
That's what you did. So your rigid particle will never show you viscoelasticity. So the viscoelasticity was put in by hand by putting polystyrene particles. But if you just wanted to change the length scale, you could just take silica particles and put in a little of different pHs, and you could tune the length scale. Yes, that's possible. But you'll never get this blisters for silica particles. It's only going to crack, but crack at different length scales.
Yeah. You told we have to, let's say I apply stress below the critical stress and then just do that, just get it down, then up, get it down and up for some time. You also told that this crumpling has a say. So there might be weak spots if I do this thing, like the critical stress might come down when it actually peels.
Absolutely true. So if I do if I go near to the critical field and do an oscillation in my field, I'm going to weaken the whole system up. So I don't have to do that. So all that I do is, I know my critical field is, say, for example, at 100 volts per microns, for example. I go up to 90 volts, come back. Go to 90 volts, come back. Third time that I go to 90 volts is going to fail. So every time that I go to 90 volts is actually weakening the system. Yes, so these are complicated time-dependent events which you can actually see up here, but we have not actually gone into the time-dependent events. Yes, there's a lot of hysteresis in the whole event here.
You see these desorption events even when you start out with a very sparse collection of particles. So in other words, you don't have a thin film, but you just have particles scattered on it.
So you'll see the reason that if I have a single particle on a colloidal, on a thin film, I can never see it. The reason is why do you have a stress in the system? The stress is there because I have a dipolar interaction. So I need two dipoles side by side to actually give me an interaction. So if I just have one single particle, I don't have the dipolar interactions. But if you have 2-3 dipoles, obviously you can see it. There's no problem.
I believe that this adsorption is dependent on the different type of surfaces. I mean, it depends on the different type of surfaces. More oftenly, what we see in normal life, that we don't have the semiconducting surfaces, and we have normally the insulating surfaces or the different type of surfaces. But what would be the effect on such type of phenomena if we change the nature of the surface?
So here my two surfaces are not dependent upon the electronic properties as such, as to do with how deformable the structures are. So I'd say even everything has the internal degrees of freedom. So silica also has internal degrees of freedom. It just happens that they are phonons. I'm talking about internal degrees of freedom, which actually changes the structure of the substrate. It's something which squashes a bit. The polymers can slightly move about. So the contact area can slightly change. For example, this problem was studied way back by Coulomb. So what Coulomb figured out was that if I had this as a duster, the old duster, the wood duster, I put it up here, I measure the coefficient of static friction. And we have learnt in our textbooks that coefficient of static friction is a number which does not depend on almost anything. And certainly not on time. So he said that, well, if I measure this coefficient of static friction, saying that this wood had made contact with this wood, say for a time 1 hour, then I would get one value. Say this experiment was done, having these two woods made contact with each other for 2 hours, then the value would be different. And he found out that the coefficient of static friction was dependent logarithmically on the amount of contact time that you had kept. So in all these experiments, what is the parameter which is most important is not the electronic properties. I mean, sure enough, the electronic properties will play a role in some point, some details, but it's how deformable these objects are. So take two very hard objects which is not deformable over time scales that you can think of, then this time dependence will go away. If you take deformable objects, very squishy kind of objects, then the time dependence will be very pronounced. So that's it.
Are there any other questions? If not, let's thank Shankar Ghosh for sharing with us his successes with failure.